This is a video for Chapter 6 Correlation, and it's Statistics 1. You should have the booklet, and on the front of the booklet there are boxes to show what you should learn by the end of this booklet. So the first thing that we're going to look at are scatter diagrams. So show diagrammatically pairs of observations of variables. So that just means being able to draw scatter diagrams. Then we've got to be able to interpret these scatter diagrams for positive, negative, or no correlation. So if that's a relationship between two variables. We then need to be able to have a numerical measure, and that numerical measure is called covariance. And that means that we get a number and we're able to see if it's a positive, negative or no correlation. It helps back up what the diagram says. Then we've got to be able to use coding as well, and the other important new thing that you'll have is the product, moment, correlation, coefficient, and we just abbreviate that to PMCC. And we've got to be able to interpret that as well. So you've come across GCSE correlation when you've done statistics, and these diagrams should not be unfamiliar to you. So in the first one, positive correlation, second one, negative correlation, and the third one, absolutely no correlation at all. We can't see if there's any, as one variable increases, the other does not. And what we try to do is draw a line of best fit, and it looks something like that for positive. So you've got a positive gradient, and in the next graph you've got a negative gradient, which looks, you would draw a straight line and you would have a negative gradient there. And the first one's a positive gradient. And you can see on the last diagram we can't draw anything in terms of a straight line. There seems to be no relationship between both of them. Let's look at the first example then. I'm assuming that you can actually draw a scatter diagram. So in the first part you've been asked to plot a scatter diagram here, so that's just simply from GCSE. So if we look at the diagram, we just need to put a scale on our axes. We need to label our axes as well. So we need this, the correct scale. And we need a title. So this one is population density. And the next one, the horizontal axis. That's the distance from the centre of the city or the town, and that's measured in kilometres. And what you will find is that there is a straight line that you can draw, and it looks something like that. I'd expect you to plot the points. So for the first one, it looks like there. Then we've got another one down here, and so on. So that's just plotting scatter diagrams. For the second part, it asks you to describe the type of correlation. So the description of it would be a negative correlation. And it says to interpret that, so you've got to take the mathematical negative correlation and turn that into a meaning in the real life situation. So what you can say is, as the distance from the centre increases, the population density decreases. So that's really quite important. They might ask you that, well they will ask you that in an exam type question, is to be able to describe the correlation and actually explain what it means. We can be a bit more exact with our scatter diagrams, and if we draw a horizontal line, which is the mean of the y values, and a vertical line for the mean of the x values, then we get what's called first, second, third and fourth quadrants. So that means that when you have got a positive, or you're drawing a line of best fit for this diagram, then you'd see that the line of best fit goes through where the axes intersect and in the first and third quadrants. We could do exactly the same thing for a negative correlation, and again we've got the mean value of the y's, which is a horizontal line, and a vertical line for the mean of the x values. And this time when you have a negative correlation, if I can draw a straight line, it goes in the second and the fourth quadrant. And you can see on the third diagram, when there's no correlation, then the points are all over the first, second, third and fourth quadrants. If we now move on to another example, we can see that we're actually been given a scatter diagram. Now in an exam situation, what would happen is you'd probably be given the diagram and you'd be asked to plot maybe 1 or 2 points, so you wouldn't have to do it from scratch. So what we've got here is the scatter diagram that shows the pulse rates in beats per minute and the breathing rates in breaths per minute of 12 people. And what we've got here, if you notice at the origin, is a new origin, so it doesn't actually have to start at 0. First part, describe the type of correlation. So you've asked to describe it. Well, we can see here, if we drew a line of best fit, we've got a positive correlation. And then if we're asked to interpret, so that's your key word here, interpret the type of correlation. So that means that you've got to interpret the real life situation. So as the breath rate increases, so does the pulse rate. We could have said that the other way around, as the pulse rate increases, then the breath rate. But we usually take the x-axis, which we'll look at a little bit further on as the dependent variable. We usually take the x-axis first and then describe it in terms of what's happening on the y-axis. I'd like you to do a little practice on that. So on exercise 6a, I'd like you to do question 2 and question 5. If you're happy with drawing the scatter diagram and just doing the interpretation, then that's absolutely fine, because I'm sure you've done this at GCSE anyway. Right, we're now going to move on to measures for the variable 4. Bivariate data. So from chapter 3 we know all about variance, and the equation that we've used before has been this one. And in correlation, we use S with a subscript of XX, and it stands for the sum. And so the variance is just your SXX divided by N, and similarly that's what you do with SYY. And this quantity is known as the covariance, and these are used to find out how X varies with Y. So that's two variables, X and Y, and how they vary themselves to each other. Right, moving on to example 4 then. The head circumference in centimetres X and gestation period in Y for newborn babies at a certain clinic over a period of time were as follows. Find SXX, so that's the covariance. So what do we need? We need the sum of X minus X bar, all squared. And we know that X bar is the mean, so we add everything, all the X's together, and so on, and we divide that by the number of pieces of data, which is 6, and we get X bar to be equal to 31.85. We then take 31.1, take away the mean, so this is your X minus X bar, 31.85, and we square it. Then we add on, and what we're doing here is we're just taking the sum of each piece of X data and subtracting the mean. Now usually in an exam situation, SXX would be given to you and you're just expected to work with it, so you need to understand what it is. So our next piece of data is 33.3, take away 31.85 and square all of that. Then the sum of 30.0, take away the mean and square 31.5 and square and the last piece of data and when you calculate those all out it's 0.5625, 2.1025, 3.4225, 0.1225 plus all the other ones, and eventually that comes to 18. So S subscript XX is 18.855. So that's covariance that we've calculated. Let's move on to example 5. Once we've looked at an easier way of calculating S subscript XX, so the covariance of YY and the covariance of SXY. And just as we did before, we found an easier way of actually calculating the variance, and it's an awful lot easier. So the ones that we have to know about are these ones, that one, and then moving down there's quite a few more. So altogether we've got 5 of them, and all of these are given to you in the formula booklet. So all of them are given to you in the formula booklet, which is quite a relief because they do take a bit of memorising. Right, example 5 then. We need to work out the covariance, so we're asked to find SXY. So if we look back at the formula, it was the sum of all the x's times all the y's minus the sum of x's times the sum of y's all over the number of pieces of data that we have. So if we put this into the formula, we've got the first part is 31.1 times 36 plus 33.3 times 37, and again I'll put that in a bracket, put that in a square bracket I think, plus 30.0 times 38. And if you're asked to do this in the exam, you will get method marks for showing this, times another 38 plus 35.0 times 40 and plus 30.2 times 40. So that part there is your sum of x times y, and then you've got to take away the x's times the y's all over 6. So the sum of all the x's, so that's the first part, 31.1. So it's just quite a bit of number crunching going on here. You've got your calculators, it's fairly straightforward. You've just got to make sure that you haven't made any daft mistakes plugging these in. Now we're going to multiply that by all the y's, the sum of all the y's. And then we're going to divide all of that by the number of pieces of data that we've got, which is 6. Now working that out on your calculator, you should get 7,296.7 minus 191.1 times 229 all over 6, and that works out to be 7,296.7, take away 7,293.65. So the covariance is equal to 3.05, and we're going to interpret that in a little while. Right, just for a little bit of practice on that, I'd like you to do on exercise 6b, question 1, 2, 3, 5, 6 and 8. Now this is used when we do covariance, it's used to find the product moment correlation coefficient, and it's given a letter, little r. So we actually abbreviate that to product moment correlation coefficient. And you can see here that it uses 3 sets of covariance. And what you'll usually find is that these values of S subscript XX, XY and YY are usually given to you, and what you need to do is pop it into that equation, and it is actually given, so don't worry about memorising that either, it's given. And what do we know about this? Well, if the value of R lies in between -1 and 1, and that means if R is equal to 1, you've got a strong positive correlation. If you've got R is equal to -1, you've got a strong negative correlation. So this is where the graph and the calculation together, you can see how strong the correlation is. If you have R equals to 0, then there's absolutely no correlation at all. So that's the 3 values. So it can be on that scale from -1 to 1. So if you do a calculation there and you get a value of 2, you know you've done something wrong. Right, let's have a look at all the things that we've been asked for example 6. The number of vehicles, etc., etc. And we're asked to calculate the value of R. So calculate R and interpret this value. So that's the sort of thing you'd be asked to do in an exam situation. But as I said, these values of covariance would probably be given to you, and then you've just got to do some substitution into equations. So I'm going to give you some of these values so that we can do a calculation for R. And the following data is available. So we have Sxx is equal to the sum of x squared minus the sum of x all squared over n. Now I've worked out x squared, the sum of x's and everything from before, so we know these values. Just to save on a bit of a calculation, I've worked these out to be, and you can check them just to make sure, so you can work out everything you need in the equation. The sum of x's 2576.47, and as I said before, these are usually given to you because you've not got enough time in an exam situation to do all the number crunching. And the other thing that would given to you would be the sum of x times y is 9915.3. So this here is usually given. Let's see if we can work out Sxx then. So that's going to be, if you pop the numbers in, I'm just going to do it straight away, it's 490.23. Do not round in any way whatsoever. You need to keep the full value of your calculation on there. If we then work out Syy, it's the sum of the y squared minus sum of y's all squared over n, and that works out to be 9034.93. And then if we work out the covariance of x and y, that's the sum of x's times y and sum of xy all squared over n. And if we pop that into the formula, we get 1907.63. So just make sure that you show all the calculations. That part's really important. So these feed into here and show all calculations. So we want to work out what R is, and R is given in the equation, remember, so it's the covariance of xy over the square root of the covariance xx and yy. So take those values, pop them in, and you get 1907.63 divided by the square root of 490.23 times 9034.93. So R is equal to 0.906. Now, as we said before, R lies in between -1 and 1, and this is very close to +1. Therefore, we've got a positive correlation. And if we look back at the table, we've got the number of vehicles and the number of accidents. So the greater the number of vehicles, the greater the amount of accidents. So that's what it means if we interpret it. So if we look at the positive correlation, it means the greater the number of cars, then the greater the number of accidents. I think instead of cars I should say vehicles. You should stick with what we've got. So if we look back at the table, we started off with the statement, the greater the amount of vehicles, because that's your x value, and then we relate that to what's happening with the accidents. So to do a little bit of practice on this, what I'd like you to do is on exercise 8b, the questions 1, 2, 3, 5, 6 and 8. And that's to give you a good idea of how to work out the coefficient R, which is the product moment correlation coefficient. So just to recap on the product moment correlation coefficient, or its value, if the value of R that you calculate is equal to 1, we have a perfect positive linear correlation. So that means as one increases, the other increases, and we get a nice positive gradient that is equal to 1. If it's equal to -1, if R is equal to -1, then it's a perfect negative linear correlation. So as one variable increases, the other decreases and vice versa. And then looking at the product moment correlation coefficient R is 0, then there's absolutely no linear correlation. I think that's the important part there, no linear correlation. But that doesn't exclude any other type of relationship there might be, because you could have a circle or an ellipse, as you can see here, or we could have a parabola or a cubic or anything like that. So linear is not the only type of relationship that you actually get. Let's look at example 7 and see if we can see what's happening here. I think there might be a little bit of a typing error on the last one here, and I think that should actually say minus 0.31. So what we've got to do is match the diagrams with the product moment correlation coefficient. So remember, we abbreviate that to PMCC. Right, we want 0.97. So that's quite a strong positive correlation, and I think you'd agree that that is a figure A. Minus 0.94 is a fairly strong negative correlation, so that looks as though it could be B. Right, 0.55, so we're looking at a positive correlation that's not that strong, so that's going to be C. And then D, minus 0.31, well, very, very weak negative correlation, so that's D. One thing that we've got to be very careful with, there are limitations with this coefficient R, the PMCC, because you could actually get a variable, or two variables rather, that do have, or seem to have, a correlation, but there is no causation, and that means one may not cause the other, so be careful. Example 8. The number of cars on the roads has increased and the number of DVD recorders bought has decreased. Is there a correlation between the two variables? Well, it looks as though as one increased, the other decreased. That could be a negative correlation. But hold on a minute. If you buy a car, does that mean the number of DVDs sales actually decrease? There's no, you've got to think of the real life situation. So there's actually no correlation, because buying a car doesn't necessarily mean DVD sales decrease. And watch out for media, newspapers, TV. They will try and put statistics forward that have a correlation, but you've got to think a little bit deeper about it. Looking at example 9. Right, over the past 10 years, the memory capacity of personal computers has increased, and so has the average life expectancy of people in the Western world. Is there a correlation between these two variables? Well, the two really aren't connected, but both have got better. There is an increase in them simply because there's been scientific development over time. So that's about all you can say with that, really, because there have been scientific advancements, and especially in development of computers. You can now have your phone can be a little computer as such, and it's got quite a high capacity, whereas back in the early times of development it filled a full room. So let's see what we can say there. And also life expectancy, people are healthier, there's better drugs, all sorts of things that go there. So one doesn't cause the other, so that's what we mean by causation. There's no connection between them, even though both of them have actually increased. So the two are not connected, but both are due to scientific development over time. So just be careful about causation. So in exercise 6C, the questions I'd like you to try there are 1, 3, 4, 6 and 7. Now we've just got the last bit to do here. If we have a look on, that's your exercise 6C to do the questions on. And then to do the coding part, this is the very last part now. And what you've got to know about coding with the PMCC, we'll abbreviate that again, PMCC, is it is unaffected by either subtracting, adding or dividing or multiplying. So there's absolutely nothing that changes when we do coding. And remember, coding was used to simplify the numbers, that's all. So what does subtracting and multiplying by a number in x and at y actually represent? Well, subtracting moves either x or y on their axis, and multiplying just changes the scales. That relates to the transformations within C1 that we've done, transformations of curves. So subtracting moves x and y along their axes, and multiplying changes the scale. So if you think about it, it's a measure of the gradient. The gradient's not really changing at all. You're still going to get some line of best fit that gives you a product moment correlation coefficient R. So that's really important. We can write them like this for the coding, and it's not affected by coding at all. First example then, calculate the product moment correlation coefficient for X and Y. Use this coding. So let's pop in what we've got. P is equal to X minus 1020 and then dividing by 1. So we can do that by popping the numbers in. So P is 0, then 12, 8, 14, 3 and 18. And if we add those all up, that is equal to 55. If we then do Q, Q is take your Y value, subtract 300 and divide by 5. So that's 4, 7, 9, 11, 12 and 16. If we add those all together, we get 59. P squared, just a bit of number crunching. So all we're doing is we're squaring that first column. 64. And that would give us 737. And then for Q squared, we add all those together and we get 667. And P times Q, 0, 84, 72, 154, 36, 288, and that's all equal to 634. Right, from that then we want to work out our product moment correlation coefficient. And thinking back to our formula for it, R would be equal to S PQ, so the covariance of P and Q, divided by the square root of SPP and SQQ. So if we work out what SPQ is, it's 634 minus 55 times 59 over 6. So SPQ is equal to, and then SPP is equal to 737 minus 55 squared over 6. So SPP is equal to, and then SQQ is equal to 667 minus 59 squared over 6. Now working those out on your calculator, that would be 93.17. Now do not round, keep that on your calculator, really important. Never do any rounding until the very end. And then the last one is the square root of 232.83 multiplied by 86. Now that's lots of decimal places as well, and 86.83, lots of decimal places. You don't have to write them down, but if you put the dots on, then that makes sense. And then that means that R is equal to, now write down your full display on your calculator and then round it to 3 significant figures. If in doubt, always 3 significant figures. So what we can see there is there's not a strong positive correlation, but there is a positive correlation for this set of data. And if we knew what the data represented, we could see if there was causation involved there, which it looks as though it might be. What I'd like you to do with exercise 6D then is question 6, please. So So can you do question 6 on exercise 6D? All the information is given to you, and that's your absolute bare minimum. I think that should be enough for the coding. As preparation for the exam, so that's exercise 6D that I've asked you to do one question, and we've got answers at the back, so you can actually check your answers for chapter 6 and then keep on going. There's a mixed exercise that you can do. So as you've gone through this video, you can actually do the questions and then check in the back of your booklet or on this. If I go, so you can pause the pages as I've gone through there and check your work, especially on the mixed exercise at the end. On Friday, I'll check that you've actually gone through this, watched the video and done the questions. I will also have some exam questions for us to go through on Friday, and that's in preparation for the S1 mock the week after. So I'm expecting you to get through all of this, and if there's anything that you've got stuck on, then you must bring it to the lesson on Friday and we'll go through it.